Hey, what's up, guys? It's Dan from SageMathTutoring.com. I have another review sheet from a student who has a test coming up, and I'm just going to do some of these problems and sort of think out loud. Hopefully, my student can kind of understand the thought process behind the answering of these questions. And hopefully, for those of y'all who are not my students, this would be helpful for you as well. So, there's basically some pre-calc stuff. It's in the beginning of the year. And let's look at the first problem. So state the domain of each function. So the domain is the set of all x values that would be represented on the graph. And when you're trying to figure out what the domain is, it's often helpful to maybe assume at first that the domain could include everything, but then ask yourself, okay, well, are there any restrictions? Is there anything that that x could not be given the situation? Now, when it comes to problem number 1, 5x squared plus 2x minus 1, the domain could be anything there. And the reason is because that is some parabola type thing. It looks like that maybe. And the way that parabolas go is that they go out forever to the left and out forever to the right. So that is a domain of negative infinity over here and positive infinity over here. So for problem number 1, that's just a straight up situation where it is negative infinity, positive infinity. Now, how did I know that it's a parabola and there's no weird stuff going on? Well, first of all, it's a one-story building. There's no rational anything. Like you see how these have fractions. Those are two-story buildings. There's no square root stuff. It's just a one-story building, and the leading exponent, the highest exponent, is 2. That is a quadratic function, and quadratic functions, unless there's some other weird stuff going on, is going to be some sort of parabola like that, and parabolas always have a domain of negative infinity to positive infinity. So that's how to deal with number 1. All right, so looking at number 2, h of x equals 1 over x minus x plus 2. So I'm actually going to write that right now. So h of x equals 1 over x minus 3 over x plus 2. So basically, this is a clear case where the x is present in the denominator of the function, here and here, it so happens. And whenever there's an x in the denominator at any time, that represents a restriction on the domain, because the bottom line is we know that we are not allowed to have zeros in the denominator. So we need to sort of root out the x values that would cause the denominator to be 0. So for example, with this one, if x was 0, well, this whole denominator would be 0, and in which case, the universe would collapse essentially. You would have an undefined fraction, and you can't have that. If this x was a negative 2, then clearly we would have a 0 here in the denominator, and that would cause an undefined fraction over here. So really, we know for a fact, let's say we don't know the domain yet, but we know for a fact that x can't be 0 or negative 2. So that's just a fact. Now, the question might arise, well, how do I represent that with interval notation? My teacher likes me to represent the domains with interval notation, so how could I represent this situation with interval notation? And basically, I like to liken this kind of scenario to a number line situation. So I imagine a number line that includes everything, except there is a hole at negative 2 and a hole at 0. Okay, so this little circle is a hole. It's not a 0. Okay, that's a hole. And here are the actual numerical values. That's a 0, that's a negative 2. The 0 corresponds with this 0, this negative 2 corresponds with this negative 2. And basically, if you look at the number line, you have all the stuff to the left of negative 2 represented, you have all the stuff that's in between negative 2 and 0 represented, and you have all the stuff that's to the right of 0 represented. So I think that is a nice visual that can really help us see that we are dealing with a domain of negative infinity all the way up until negative 2. Notice how I am not including negative 2, right? And then we're going to combine that. Some teachers like to use this notation for a union. That would be combined with negative 2 all the way up to 0. right here, and this part recognizes this section right here, and then finally it would be a union of that with 0 all the way to positive infinity right there. And this section represents this right here. So that is the domain for this one. All right, so looking at number 3, we've got f of x equals the cube root of x minus 4. Let's see, cube root. Well, you know, if it was the square root of x minus 4, then we would have a clear restriction, because anytime you take a square root, you can't take a square root of a negative number. But I think the teacher is trying to be a bit sneaky by making this a cube root, because the bottom line is you could actually take a cube root of either a positive or a negative number. That's totally fine. So the domain for this one, since you could take a cube root of both a positive or a negative number, then the domain, it could be anything. So the x values that could be represented in the domain, therefore, would once again be this. Now, I think it's probably helpful for me to show what would have happened if this was a square root. So had this been a square root, it would have been this, right? And the fact that there isn't anything written here implies that there's an invisible 2 written in there, which means that it's a square root. Basically, x minus 4, you got to have a situation where whatever is underneath the radical, it can't be negative. Otherwise, you would have an imaginary number. Now, what's another way of phrasing can't be negative? Well, another way of phrasing can't be negative is that it has to be greater than or equal to 0. Okay, you can say that it has to be positive, but you have to remember that it could equal 0. So this could equal 0 because, you know, square root of 0 is just 0, so that's fine. So basically, since you know that this can't be negative, therefore it has to be greater than or equal to 0, and you could, in a sense, just go off to the side and force it to be greater than or equal to 0 with an inequality. All right, so from here, what I would do is I would literally just solve the inequality. It would have x is greater than or equal to positive 4. And in a way, that's your domain right there. But again, your teacher probably wants you to write the interval notation. So what I would do is I would go off to the side. I would very quickly draw up a number line. I would write a solid dot at 4. You know, keeping in mind the zeros over here or whatever. But we're only taking into account one single critical value, and that would be 4. And then recognizing that x is everything greater than that, greater than or equal to that. And that visual provides me with a decent way of seeing that the domain in interval notation would be brackets for positive infinity. And first of all, remember with the infinity symbols, whether it's positive or negative infinity, you're always going to have the parentheses next to it no matter what, okay? And in this case, we have 4, and it's brackets because 4 could be included as denoted by the solid filled in circle there. So that's what we would have done with a square root of x minus 4. Once again, with problem number 3, it is a cube root of x minus 4, so we don't have to even worry about any of this because the cube root can be of a positive or negative number. Okay, looking at problem number 4. I'm just going to kind of focus here for a second. We have 10 over x squared minus 2x. So similar to problem number 2, we have a scenario where we have a denominator to contend with, and we have x's in the denominator and so on. And this is a case where, once again, we might have an undefined scenario, and we have to root out what are the x values that would cause this fraction to be undefined. Well, that's actually very easy. We're going to take this, expression, x squared minus 2x, and temporarily, let's just force it to equal 0 temporarily. And this is a way of finding out what x can't be, right? So solving this is a quadratic binomial. It's a good idea to set it equal to 0 anyway. Back in the day with algebra, you may have learned that. And then we're going to factor out x because that's the GCF. We have this. equals 0. And then we ask ourselves, all right, well, if this x was 0, it would be 0 times whatever the heck that is, and it would be 0. And if this whole thing was 0, well, it would be 0 times whatever the heck that is, and that would be 0. So I think my student probably could easily see that it would be x equals 0 as one of the solutions, and x is positive 2 for the other solution. So once again, let's liken this to a number line scenario where you have an open circle at 0, and we have an open circle at positive 2. And we know, because these are the restrictions, x equals this according to this equation, but what that amounts to is that in this scenario, x can't equal 0 or 2, because if x equals 0, this whole thing would be undefined. If x equals 2, then this whole thing would be undefined. So what we're going to do is, again, bring this information down to the number line, fill in this section, because x could be all that stuff. X could be everything in between, and x could be everything over there. So what does that amount to? That amounts to the following. We've got negative infinity all the way up to 0, but not including 0, union. Not including 0 up to not including 2, union. Not including 2 all the way to positive infinity, and that is the answer in interval notation. Okay, so now we have composite functions and things like that. So let's take a look at number 5. We've got, focusing here, we got f plus g of x. What is that? Well, that's simply to add f of x plus g of x. Pretty straightforward. And then we're done because these are not like terms. All right, what about f minus g of x? Straightforward as well. That's just going to be that. What about f times g of x? So that's a little bit trickier, maybe. So that's x squared plus 5. I would wrap this in parentheses because we want to be clear that it's the whole thing being multiplied to this. I believe the teacher would probably prefer to distribute that here and here, right? By the way, for the record, I made sure I had parentheses because if we didn't draw parentheses, it would look like it's just the 5 that's getting multiplied to the radical 1 minus x, but we want to be clear, this radical 1 minus x is being multiplied times the 5 and the x squared, which, by the way, we're going to do right now. So that becomes, actually just keep it in green, it's going to be x squared times this plus 5 times that as well. So that's good with this one. Okay, what about f over g of x? Well, that would be x squared plus 5 over radical 1 over x. What I would do here is I would actually go ahead and simplify this by rationalizing the denominator. But when you first write the thing, we first wrote the obvious scenario, which is, okay, f over g. Well, that's clearly x squared plus 5 over radical 1 minus x. As soon as you write it, ask yourself, are there any restrictions on the domain? And yes, there are restrictions on the domain. 1 minus x cannot be, like this whole thing, the whole thing can't be 0, first of all, because if it was a 0, then there'd be an undefined fraction, and you can't have that. But also, there's another restriction on the domain. This 1 minus x can't be negative. So I would actually go off to the side, and I would realize that 1 minus x, well, let's just say x can't be 1. We know that for a fact, right? X cannot be 1, because if x was 1, it'd be 1 minus 1, then the whole thing would be 0. But we also know that 1 minus x has to be 0 or greater, and since 1 minus x can't be 0, we know that 1 minus x has to be greater than 0. So we're going to force it temporarily to be greater than 0. And that ends up resulting in x has to be less than 1. Now, the fact is that x has to be less than 1, because if x was 1 or more, then this would either be 0 or negative. All right, so x has to be less than 1. And that should check out. Like, imagine if x was like -2, right? Well, then, it'd be 1 minus a -2, which would be a +3 underneath here. Imagine x was 0. X, 0 is less than 1. Imagine x was 0. Well, that would be 1 minus 0, and that would be a radical 1, and that's totally fine, right? So the bottom line is x has to be less than 1. We also know that x can't be 1. But this statement already covers that. This statement already covers that, right? X is less than 1. So this is the MVP restriction, I would say, when it comes to the domain of this function. So what I would do is I would simplify this, rationalize the denominator, which I'll do in a second, but I would include this statement in the final analysis of this function. And in case that's not clear, I'm going to make it clear now. Hopefully this is along the lines of what the teacher is doing with my student. There's always a risk that I am emphasizing something that the teacher is not emphasizing. So we have radical 1 minus x over radical 1 minus x in order to rationalize the denominator. We're going to take that up here. So this becomes x squared times 1 minus x plus 5 times 1 minus x. And then down below, we have the 1 minus x. So that ends up becoming, I'll do an equal sign to, help us remember that it's still f over g of x equals this. So you can say that this is like the simplified version, because it is, but I would also add, something like with x being, I would maybe say like all x being less than 1. All right, I would squeeze that in there, because we don't want to, even though we simplified it, we don't want to forget about this original moment where we had this denominator of radical 1 minus x. You don't want to just pretend that that didn't happen along the way. So again, as soon as you set it up, take note of the restrictions on the domain, write them down if you have to, right there, and then go through the simplification process. All right, so that's one way of handling this one. Okay, and then we have the composite scenario. So that would be f of g of x. And I had told my student before, look at the letter that's on the outside. That's the overarching structure. That's the skeleton of the whole thing. So since f is on the outside, we're literally going to write f of x, only instead of an x, we're going to put a big parentheses. And then when asking ourselves what goes inside the parentheses, well, that would be g of x goes inside. So we're going to put what g of x is, which is radical 1 minus x. I would pause here, ask myself, are there any restrictions on the domain? Well, absolutely. This 1 minus x cannot be negative. In other words, 1 minus x has to be 0 or greater, right? So I would write 1 minus x has to be greater than or equal to 0. And I would solve for x where this ends up becoming x has to be less than or equal to 1. I would make that mental note right now. X has to be less than or equal to 1. And then I would carry on with simplifying this. So let's go ahead and square this thing. By squaring it, you would end up with 1 minus x plus 5. And then that would end up becoming negative x plus 6. So the final analysis would be f of g of x equals negative x plus 6 with all x being less than or equal to 1. All right. So I changed the order here just to have x on the left, but it's still x is less than or equal to 1 over here. Well, it's x is less than or equal to 1 over here. And the reason for that is because if you were to plug this into your calculator and graph it, you would realize that the graph, like, that's the origin right there. You know, if you were to just graph this, I mean, it would be like something like that, right? Something like that. And but the thing is, because we had this previous restriction on the domain, it's not that. Okay? It is actually something like that. Okay, I'm going to erase that little part there. It's something where it's like that. All right? Because you can't have x values greater than 1. So it would really be a graph that is a line that goes on forever in this direction, but it stops right there. Okay? Now, had we not taken into account the restrictions on the domain, we would have taken a look at this simplified version of the function, and we might have made the mistake of graphing the whole line. All right, hopefully that makes sense. Okay, focusing on problem number 6. Let's take a look at that. Shrink this down a little bit, give myself some more room. So, okay, f plus g of x, that's going to be 2x minus 5 plus x all over x minus 1. Done. F minus g of x, that's going to be 2x minus 5 minus x all over x minus 1. That's done as well. Not too bad, right? Those first two ones are pretty easy. So let's look at, therefore, the other ones. F times g of x. We'll do that over here. F g of x. Well, that's going to be a matter of multiplying 2x minus 5 times x over x minus 1. Now, when we simplified these guys, the x minus 1 remained below in the denominator, so you could just look at the function and know that there's a restriction where x can't equal 1, because if x was 1, there'd be a 0 here, right? And that's a big no-no, so x cannot equal 1. Well, this is a scenario where we're multiplying stuff. I'd be concerned that, like, for example, if that was a 5x minus 5, then you could simplify this, and then the x minus 1 would cancel. So I would just be very, very clear that x cannot be equal to 1. So I would go off to the side and just be like, x can't be equal to 1. And I would just have that as a mental note as I proceed with simplifying this stuff. Now, when I simplify it, probably helps for me to realize that there's an invisible 1 in the denominator, because therefore it's a fraction times another fraction. What do you do when you multiply fractions? You multiply straight across. So multiplying straight across would give me 2x squared minus 5x all over x minus 1. Now, it so happens that I can't cancel this x minus 1 out. There might be other scenarios where you would be able to cancel the x minus 1 out with the top, all right, like by factoring out a GCF and then canceling the x minus 1 out. Now, we can't do that here. It so happens that we can't. Now, there are other scenarios where you could cancel out the x minus 1, which is why it's good to make this mental note right out the gate. As soon as you write this first part, take note of the domain restriction. Write it down somewhere, because you might have to mention that towards the end after simplifying everything, because you don't want to forget that x still can't equal 1. Even if you were able to cancel out the x minus 1 down below, you don't want to forget that x still can't equal 1 based off of this first piece of information. All right, so what else do we have? We have f over g minus x. So let's see, f over g, not minus x, it's of x. So that would be 2x minus 5 over the whole thing of x over x minus 1. Okay, so we got a lot of domain restrictions here. First of all, this denominator can't be 0, so we know for a fact that x cannot equal 1. Secondly, we know that this x minus 1, well, that's all we need to know about that. This x can't be 0, because if this was 0, then the whole denominator would be 0. So we also know that x cannot equal 0. So these are two pieces of information that I would make a mental note about, all right, when I proceed from here. Now, Let's simplify this. Once we have those domain restrictions and we know for a fact what they are, we can simplify this. Now, what the heck's going on? We have some number divided by a fraction. Well, what would we do under normal circumstances if we had some number divided by a fraction? Well, that is a matter of realizing that it's really 3 divided by a fraction, so it's really 3 divided by 1/2, which is really 3 times 2 over 1, which of course is 6. And so what do? We took this number and we multiplied this number by the reciprocal of this number. So you could take this number, flip it upside down, and smash it into the top number, in other words. So that is what we're going to do with this. We're going to take this number and we're going to multiply this number times the reciprocal of that. So we'll do that over here. So that would end up being f of g of x equals 2x minus 5 times x minus 1 all over x. And there is an invisible 1 underneath here, so that's going to be this times that all over 1 times x. So the top would be a FOIL scenario, so that's going to be 2x squared minus, well, there's definitely going to be a positive 5 over here. And let's see, we've got negative 2x combined with a negative 5x. That's going to be a negative 7x all over x. Now we have the domain restriction here as well, that x can't be 0. But we already took that into account. So the final analysis, I would say, is this, but I would also include the fact that x cannot be 0 or 1. Okay, and then looking at f of g of x. The overarching structure is f, so that's going to be 2, empty parentheses minus 5. What goes inside? That would be x minus 1. Let's see, we have a domain restriction where x cannot be equal to 1. We could just kind of make that mental note right now. Simplifying this gives me 2x over x minus 1 minus 5. We're good to go there. That's it. All right, and if you want to mention the domain restriction, that's fine, but at the end of the day, you don't really have to, because it's not like we canceled out the x minus 1, so the domain restriction in the final analysis should be obvious to anyone who knows what they're doing. So we could just leave it like that, but if you want to kiss the teacher's butt, you could, mention that, by the way, x can't equal 1 either. Look, I'm smart, yay. All right, looking at this final problem, we've got f plus g, I'll just write a. I'm tired of writing the f plus g notation. So that's going to be x equals x over x plus 1 plus x cubed. Guess what? You're done. Maybe your teacher would prefer you to write the x cubed first, though, because that exponent is larger. So that's that one right there. Okay, b is going to be x plus 1 minus x cubed. You could write it like that, or you could write it like this. And these are not like terms, so you can't combine them, so we're good to go with that. All right, c would equal, let's see, that's multiplication, so that's going to be x times x plus 1. I'll wrap it in parentheses. I like to sort of separate things out. And we have this. Are there any restrictions on the domain? Yes, there are. Maybe make that mental note. X cannot be equal to -1. So we're going to keep that in mind as we proceed. Multiplying this straight across, keeping in mind there's an invisible 1 underneath there. So it's really just multiplying 2 fractions straight across. And when you do that, you multiply the numerator times the numerator. So that's going to be x to the 4th all over x plus 1. And believe it or not, that is all you need to write right there. That's the final situation for f of g of x. Okay, let's see. D would be division, so that would be x over x plus 1 divided by x cubed. All right, so now we have some restrictions on the domain. Let's start from the bottom. Clearly, x cannot be 0, because if this was 0 cubed, then it would be an undefined fraction. So we're going to make a mental note of that. X cannot be 0. Making that mental note. Is there anything else that x can't be? Well, yes, we have another denominator here where it's like x can't be negative 1. So x cannot be 0 or negative 1, because if this x was a negative 1, then this would be a 0, and that's a problem too. Okay, once you make those mental notes, now let's go ahead and simplify this situation. I'll write equals. So bringing it up here, that's going to be x over x plus 1. That's a fraction divided by x cubed. Now, this is some fraction divided by a number, right? Now, what do you do under normal circumstances? If I had some fraction divided by some number, well, that's the same thing as the fraction divided by the whole number with 2 over 1, which is the same thing as 3/4 times the reciprocal. And I would take it from there. So that would become 3/8. Now, what just happened? It's almost as though this little number just morphed into this guy, and these two guys just got multiplied together, and we ended up with 3/8. So we could take this x to the third and multiply it by just the x plus 1, okay? And I'll just do that right here. That's going to be x over x to the fourth plus x to the third. All right? Because I distributed the x to the third here and to the 1. All right? So in my final answer, I would write x over x to the fourth plus x to the third, and I would also write in there that x cannot equal negative 1 or 0. All right, now in this case, yeah, just write that. Okay, at the very least, that'll kiss your teacher's butt. It is implied by looking at this because nothing canceled out. So hopefully anyone that knows what they're doing would see that x can't be negative 1 or 0, but just whatever. You could write it. That's fine. Not a big deal. Okay, and looking at f of g of x, once again, f of x is the overarching scenario, so I'm going to rewrite it. Only instead of x, I'm going to write empty parentheses. Just do that. Use tunnel vision. Do one thing at a time. What do I fill it up with? I fill it up with g of x. What is g of x? G of x is this. And that one's fairly straightforward. I mean, that one, it just ends up becoming x to the third all over x to the third plus 1. All right? It's an ugly 3. That's it. Okay, done. Okay, algebraically determine whether the function is even, odd, or neither. Okay, a function is even, like let's say we've got something like this. Let's call it f of x squared. Well, we'll say f of x squared plus 3. That's fine. You know it's even if you can plug in a negative x and you end up with the same damn function that you started with. All right, this would end up becoming this. Well, isn't that the same as this? Heck yeah. That's how you know it's even. How do you know when something's odd? You know when something's odd if you have a function and you plug in negative x and you end up with the negative version of what you started with. And here's what I mean by that. This is going to be negative x cubed plus x. And if you think about it, that's really negative parentheses x cubed minus x, right? Isn't it? Because I could factor out a negative 1 from here and from there, and I would end up with negative x cubed minus x. Well, here's x cubed minus x. Here's negative x cubed minus x. So if you plug in negative x and you go through the motions and you end up with the negative version of this, also known as negative x cubed minus x, then it's odd. All right? So quickly, let's make sure we understand that, well, this is even, this is odd. All right? And let's just get this over with. All even functions are symmetrical about the y-axis. Okay? All even functions are symmetrical about the y-axis. With my student, we were kind of all over the place. We didn't get a chance to go over these sort of principles. All odd functions are symmetrical about the origin. Okay? Once again, all odd functions are symmetrical about the origin. All even functions are symmetrical about the y-axis. All odd functions are symmetrical about the origin. Now, the good news is there are halfway decent ways of knowing whether or not a function's even or a function's odd. And we're going to get to that in a second. However, let's also be clear. It's possible for a function to be neither odd nor even. For example, if I had something like this, and I decided I wanted to see if it's, odd or even, I could plug in a negative x to see what happens, right? What I would quickly realize as a result of going through the motions is that this would end up becoming negative x cubed minus 3. And even though this kind of seems like similar to this situation, this is actually different. Because think about it. Let's say I try to factor out the negative 1 here. Remember how I had factored out a negative 1 here? If I try to factor out a negative 1 here, it's going to equal negative x cubed plus 3, right? That is the negative of x cubed plus 3. That's not the negative version of the original function. The original function is x cubed minus 3, right? So this is not odd, okay? This is not odd because after plugging in a negative x, I don't end up with the negative version of the original function. When I plugged in negative x over here, I ended up with the negative version of the original function. Here is the original function, x cubed minus x. Here's x cubed minus x. That's the original function, and we ended up with the negative version of the original function. This is not the negative version of the original function. The original function is x cubed minus 3. This is not x cubed minus 3. All right, hopefully that makes sense. So this is neither even nor odd. So the question is there a quick way of determining whether or not a function is even or odd? And often there is. Okay, often there is. Now, here is a decent rule of thumb that you can employ much of the time. You know a function is even if all of the exponents that are like hovering above the friggin' x's are themselves even. All right. Now, notice you can have, when it comes to an even, this is an even function. Notice that you can have a constant. Okay, there's no x attached to this too. If all the terms that have x in it are such that they have exponents that are themselves even, it's an even function. And think about it. That makes sense because if we plug in a negative x, then even exponents would turn that negative x into just itself again, a positive version of x, right? So anytime you have terms that have x in it with an exponent that's even and a constant here and there, maybe, it's even, okay? But the cardinal rule is if all of the exponents hovering above the x terms are even, it's an even function. Is there a trick of the trade to let us know whether or not it's an odd function? Well, yes, you know a function is odd if all of the x terms have an exponent that is itself odd. Now, think about it. That's an invisible 1 right there. So that's an odd exponent, that's an odd exponent. So that's the first rule to know whether or not a function is odd. Now, another thing about odd functions is you cannot have a constant. Okay, you can't have a constant. If there's a constant, then it's not odd. But if it's such that it's a function that has no constants and all of the exponents hovering above the x's are odd, then it's odd. Okay, so you can't have a constant. So I can't just be like, if there was a -7 attached to this whole thing, guess what? It wouldn't be odd. All right, so that's a nice rule of thumb for quickly discovering whether or not functions are even or odd. Okay, so let's see if we can apply those rules here. Looking at x to the 6 minus, let's blow this up, whatever. X to the 6 minus 2x squared plus 3. Hopefully my student realizes that that's even based on the previous rule. How do I know? All of the exponents hovering above the x's are themselves even. It's okay if we have a constant, that's fine. Even. Next one, x cubed minus 5. That is neither even nor odd. I mean, it would be odd if this -5 wasn't there, but what do we say about odd functions? You can't have a function. All right, you can't have a constant, rather. Can't have a constant. This is a constant. 1 over x squared, even, for the exact same reasons I had mentioned before. All the exponents hovering above the x's are themselves even. Okay, now once you get into these guys, this is a little bit more complicated looking gobbledygookness, all right? Whereas these guys are kind of straightforward. You can immediately see what's going on with them and apply those previously mentioned tricks of the trade that I said, where you know something's even if all the exponents are themselves even, and maybe there might even be a constant. There doesn't have to be a constant. You know it's even if all the exponents are themselves even. You know something is odd if the exponent is odd and there isn't any constant. All right, all the exponents are odd and there aren't any constant. Now that is a good, nice kind of trick of the trade that you could use for relatively simple situations like this. However, this where there's simplification going on and radicals and this and that, you might want to just utilize probably what the teacher is saying, what the teacher told you, which is that whole thing of like, testing out what happens if you plug in -x, and so on. So let's investigate this one, all right? So if we were to be like, all right, well, what happens if we now investigate j of -x? Well, j of -x would be 2 times -x all over. And that ends up becoming -2x all over x squared, which is really -2x over x squared. So you end up with the negative version of the original function, because the original function was 2x over x squared. So this is odd. All right, hopefully that makes sense. Odd. All right, let's focus on this guy. We're going to do the exact same reasoning process. So it's like m of -x. Let's see what happens. I like to draw the empty parentheses first, and then fill in the empty parentheses with what belongs there. We're going to see what happens here. -x. Radical 1 minus x squared. Well, guess what, my friend? That is the negative version of the previous function. Because if you think about it, here's the previous function, and there's a big fat negative in front of it. Therefore, this is odd. All right, so moral of the story, when it's like a little complicated, like these guys are pretty complicated. There's cancellations, there's square roots, yada yada. Employ that sort of strategy, which is more like the textbook strategy. All right, so for this one, that's going to be h of -x equals, I'm going to draw empty parentheses first. I like to do that because I like to not make careless mistakes with regards to the negative. So we have the entire negative x being squared, not just x. And we have negative x over here, and let's see what happens. That's going to become 5 plus x squared all over negative x, which really is the same thing as negative 5 plus x squared over x. Because think about it, this negative right here could be applied to the bottom or the top, but not both, right? Now, it was applied to the bottom. Here it was being applied to the bottom, so I'm just putting it out to the side. Usually the answers in the back of the textbook will have the negative next to the dividing line. Okay, and just know that that means that that negative could be applied to the bottom or the top, but not both. And the reason I'm putting it next to the dividing line is because we can very, very clearly see now that this is the negative version of the original function. The original function was 5 plus x squared all over x. This is the negative version of that original function. Therefore, this is odd. Okay, so looking at f of x equals negative blah, 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 blah. Right. Graph f of x, label the vertex. Okay. Okay, so here's my graphing paper. Graph f of x, label the vertex. Right. Okay, good idea to make sure that all of your functions that you're trying to graph without a calculator look like this. Something along these lines. I know this could be confusing, but it's still nonetheless helpful. If you could sort of memorize this structure where it's like a times f of blah, 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 and then plus d. In this case, since it's a quadratic scenario, because I see that 2 there, I mean, it's really going to be something that looks like this. A times, let's see, b. In this case, it's squared, and then it's plus d. All right, so I took this concept and I sort of applied it down here with this exponent of 2. All right, whereas this is the more generalized concept where you have, a times the function plus d. Well, this is, the same deal where the function, the operation being applied is really a quadratic situation where we have an exponent of 2. But nonetheless, it's a good idea to make sure that it looks something like this. Now, what am I really getting at? What I'm really getting at is when you're dealing with a quadratic situation like this, you want to force the parentheses to look something like this. In other words, if there's a GCF in there, factor it out. All right. So so that you end up with just an x right here. There's no coefficient in front of the x. The coefficient has been factored out. And I'm harping on this because there is a coefficient next to the x right now, and that's a problem. Okay, that's a problem. So we're going to rewrite this right away, where our graph really is this. Okay, now it's kind of ugly looking, right? But think about it. The 2's on the outside. The x no longer has a coefficient in front of it, which is excellent. And we have a plus 1/2. So that's, a fraction, obviously. That could be a little confusing, but just know that 2 times 1/2 would indeed give me 1, which is what we have here, right? I wouldn't graph it until I did this first. So first of all, they want us to label the vertex and graph it. I'm cool with labeling the vertex right now. But you know what? I will graph it. But I kind of think it's better to identify the transformations first. All right, so let's get the labeling of the vertex over with right now. Labeling of the vertex pays special attention to these numbers. You have your positive 1/2 and you have your -4. So the vertex would be, my student's pretty good at this, I noticed from yesterday, it's -1/2 comma 4, where when you find the x-coordinate of the vertex, it's always the opposite sign of this thing. And when you find the y-coordinate of the vertex, it's always the same sign as this. So I actually made a mistake. You may have caught that if you were watching. So this ends up becoming a -4 because it always stays the same. This guy stays the same. This guy switches the sign. So we have -1/2 comma -4. So that's the vertex. And you know what? Whatever. We'll plot that right now. So let me just sort of label this real quick. Okay, so we've got -1/2 comma -4. So I'm just going to zoom in and we're going to write the vertex there. So that's -1/2 comma -4. So that's right there. All right, zooming out. What else can we do? Let's see. Identify the transformations. I'm actually going to do that first. I'm going to identify the transformations. We definitely, I'm not going to write it, but I'm just going to say it. We have a horizontal shift of 1/2 to the left. We've got a vertical shift downward 4. We actually took that into account when we did the vertex. Unfortunately, we also have other things. We have, it's a -a. So a is negative, so that means that the horns are pointing down. So we know it's a downward facing parabola. By the way, we know it's a parabola because it's a quadratic function. So the horns are facing down. We know that for sure. We also know that there is a vertical stretch of 3 and a horizontal compression and with a scale factor of 1/2, okay, by a factor of 1/2. So when it comes to the horizontal compression, my student's pretty good at this. He knows that you want to take the reciprocal of this number, and that's how much you are compressing something by a factor of 1/2. All right. In this case, whereas this is a little bit more straightforward, this is vertically stretching something by a factor of 3. All right. So how can we go about this one? Well, one thing we could sort of do, here's what I would advise, okay, and this is just me. What do we know about this? We know where the vertex is. There it is. We know that the horns point down. We know that much, right? The confusing part is the vertical stretching and the horizontal compressing. So what I'm going to do is I'm going to blow this up, and I'm going to write an upside down normal parabola, okay? A normal parabola would be such that you have 2 points here, all right, and it would go like that, downward, okay? That is the case if there wasn't a vertical stretch and a horizontal compress action, all right? It would be something like that. Now, how do I know that? I know that because under a normal parabola scenario, from the vertex all the way to the first point would be one single unit. From this vertex all the way to the first point would be one single unit over here. And from the vertex to the first point in this direction would be one single unit. And the vertex to this point in that direction would be one single unit down. All right, so that's why I have this is in the half and this is in the half as well. All right, a halfway marker right there. So anyway, let's apply the vertical stretch. It's a vertical stretch of a factor of 3. So that means that instead of a vertical distance of 1 unit between this vertex and this first point, it would be a vertical distance of 3 units. So it would be 1, 2, 3. So this guy goes from here to there. I'll make that in yellow. All right. And this guy goes from here to there also, okay? So we have these new points where it now has stretched like that. Okay, that's where we are now. All right, so that's where we are now, and I know this can get confusing, but don't fear. We just take it one step at a time. What did we just do? We just did the vertical stretch. This guy got stretched by a scale factor of 3, so it used to be 1 unit away from the vertex vertically, but now it's 3 units away from the vertex vertically, so we had to bring it down here. All right. Same with this one. We had to bring this one down here. Now we're going to apply the horizontal compression. We know that the horizontal compression is by a factor of 1/2. So what that means is if we had the axis of symmetry denoted here, right? If we had the axis of symmetry denoted, it would cut right down the center, wouldn't it? Now, when you do a horizontal compression, what are we doing? Applying that factor of 1/2, which means that what used to be a full unit of distance from the axis of symmetry is now going to get cut in half, right? This is a full unit of distance. So that's going to get cut in half, which means that the new point is going to be here. Because this green is the halfway marker between the axis of symmetry and this point. So we already applied the vertical stretch. Now we're applying the horizontal compression by a factor of 1/2. So we're cutting this distance between the axis of symmetry and this point in half. We're going to do the exact same thing on the other side, and that actually lands us on this axis. Why? Because from this yellow dot all the way to the axis of symmetry, it's a full unit. So now we're cutting it in half. Done. Okay, that is actually the graph right there. It's all in green, and it cuts straight down. All right, it's an ugly looking parabola, but hopefully you get the idea. So once again, it is the green parabola that is the graph. We had to zoom in for it to get a little bit more precise. But what did we do? We took into account the fact that it's upside down because of the negative. We took into account the vertex, which I know my student has no problem finding. In fact, you could plot that right away. And then finally, we took into account the horizontal compression and the vertical stretch. We did the vertical stretch first. You could have done both. You could have done either in either order. But it was a vertical stretch of a factor of 3, so we had to stretch it. That's where the yellow came from, and then we did the horizontal compression by a factor of 1/2, which is the green section, okay? Anyway, identify the transformations. We could have just written that. Identify the domain, range, blah, blah, blah. Okay, domain. Graphing it first is really helpful because you can clearly see what the domain is. The domain is all real numbers, also known as negative infinity to positive infinity. How do I know that? Well, that's because the domain of any parabola function, parabolic function, is, unless there's like a restriction, is negative infinity to positive infinity. So what is the range? Well, again, graphing really helps. The range is negative infinity all the way up to -4. Notice how I said negative infinity first, because you always want to mention the smaller numbers first. All right, so just remember that. Always mention the smaller numbers first. Negative infinity is smaller than -4. So that is going to be negative infinity all the way up to -4, but including -4, yeah? Because -4 is right there. It's definitely included on the graph. Intercepts. Let's see. There's no x-intercepts. No x-intercepts. The only intercepts is the y-intercept at this point 7. Now, how do I know that? I could know that by looking at the graph. Clearly, it's on 7, or -7, I should say. Clearly on -7. Another way of knowing is to go to the original function and plug in 0 for x and see what you get. You would indeed get f of 0 equals -7. So we could say, y-intercept -7. Let's see, asymptotes. No asymptotes at all. Not for this, not for parabolas. Is there an axis of symmetry? Well, absolutely. In fact, we had sort of drawn it before, right? Didn't we? The axis of symmetry is at -1/2. Okay, so we'll say AOS -1/2. Now, we could see that visually, but there is another way of doing it. The other way of doing it would be to put this in a standard form and then do the -b/2a thing. You could do that. I'm going to just trust my student knows how to do that. Moving on. So let's see. Is the inverse a function? Okay, well, there is a visual way of knowing whether or not the inverse itself is a function, and that is to imagine an invisible dotted line cutting through like that with a slope of 1/1, all right, and passing through the origin. And you could treat that as a mirror, okay? And you ask yourself, all right, well, if this was reflected across this mirror, what would it look like? Well, it wouldn't be over here. It wouldn't be all the way up here. It would literally be the same thing like over here, if you can kind of see that. So that's like a halfway decent way of knowing whether or not the inverse is a function. So let's take a look. The vertex here is -1/2, -4. So the vertex here would be -4, -1/2. So that'd be like right there. Let's see. And paying attention to the green thing. So this green dot lands on -7 on the y-axis. So we would have a dot landing here that would be reflected here. So this ends up becoming something like that. All right. Now that's not a function. And the way that I know is because it does not pass the vertical line test. Okay, it doesn't pass the vertical line test. Keep in mind this is the green function. That's the one that we're really paying attention to, and that is perfectly reflected over here. So it doesn't pass the vertical line test, so it's definitely not a function. We can know that for sure. Let's see what else they say. Explain why or why not. Well, I just did. Okay. Hopefully that's enough for your teacher. We could sort of visually show the reflection, right? If it's not a function, how can we restrict the domain of the function so that its inverse would be a function? Right, let's see. Well, that's an interesting question. How can we restrict the domain of the function? I'm assuming the original function. How can we restrict the domain of the original function so that the inverse would be a function? Well, I would rely on the visual for that also. So I think it'll be helpful for us to get rid of the yellow and black here so we could really focus on the green stuff, because that's our final sort of graph. And we want to know, how can we restrict the domain of this guy so that when we do the inverse passes the vertical line test? Well, let's get clear. The inverse fails the vertical line test because of this part and this part, right? If you pass a vertical line through this thing, it hits the function here and there, right? So that's a problem. So my thought is, this inverse would pass the vertical line test if this was gone, right? I mean, if that was gone, then it would pass the vertical line test, wouldn't it? That's one way of, making sure it passes the vertical line test. The other way of making sure it passes the vertical line test is if this one, this one was gone, right? Then it would pass the vertical line test, right? And we could carry on our way, right? So I think it's really just going to be a matter of, picking which one you want to get rid of, right? Let's say we decide we want to get rid of this, right? Leaving only this sort of top portion behind. And by the way, it goes on forever, right? Half of a parabola, it looks like, right? Half of a parabola. We got rid of this part. Well, that means that we would have to get rid of this part right here, okay? Because if we reflected this piece across, it would end up becoming this piece. So let's actually do a dotted line to represent the graveyard of what this used to be, and we'll do a dotted line representing its corresponding piece, right? This dotted line would reflect here. So let's say we got rid of it, and therefore we got rid of this. Well, then this solid part, this would be a function because it would pass the vertical line test. So a restriction on the domain of the original function would be to get rid of everything to the left of the vertex. That would be a restriction on the domain of the function. On the original function, that would result in the inverse being itself a function. So my thought is if we just got rid of everything to the left of this vertex, then the inverse would be a function. So what was the original function? Here was the original function, right here, -3, blah, 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 blah. What was the vertex? -1/2, comma, -4. So what we could say, in my opinion, we could say with all x being greater than or equal to 1/2. So that's a way of ensuring that's a restriction where x cannot be less than 1/2. Okay. So if we say all x's are greater than or equal to 1/2, what that means is that all the x's on the original function must be greater than or equal to 1/2. If that was a restriction that we were taking into account, then the reflection would indeed reflect across as this, and then we would indeed have a new inverse function that does indeed pass the vertical line test. Hopefully that makes sense. Okay, so then they say find the inverse algebraically and then graph the inverse. Okay, well, let's find the inverse algebraically right now. So finding the inverse algebraically would be a matter of taking the original function, which we could call f of x equals y equals -3. And I'll focus only on this part right here. I'm kind of replacing the f of x with a y because it will make this next part easier, as you'll see. Basically, when you want to find the inverse, you just replace the y with an x and the x with a y, and then solve for y. So this becomes x equals -3 times 2y plus 1 squared, -4. And continuing from there, let's actually just hone in on this stuff. First thing would be to add 4 to both sides, so we end up with x plus 4 equals -3 times 2y plus 1 squared. Dividing both sides by -3 would be x plus 4 divided by -3 equals 2y plus 1 squared. Let's do a little barrier so it doesn't get confusing. At this point, we're going to have to take the square root of both sides, and this is actually the moment where the inverse becomes not a function. And the reason is because when you take the square root of this side and this side, you got to do this plus minus thing. It is the plus minus thing, that plus minus moment, that causes the parabola to not only be this, but also this when you graph the inverse, okay? This is the plus part, and this is the minus part, all right? So that is, a nice piece of information for you to take into account. But nonetheless, as a result of doing that, we end up with, let's see, plus minus radical x plus 4 all over negative 3 equals, this just becomes 2y plus 1. And the reason is because this exponent of 2, when I did the square root of it, it canceled out the exponent of 2, leaving only 2y plus 1 behind. So here it is. Then I'm going to subtract this one from both sides. I'm actually going to write that out front over here. So the final, well, not the final, we're getting close. It's negative 1 plus minus radical x plus 4 all over negative 3. But that equals 2y. And then from there, we are going to have to divide everything by 2. And then we end up with y equals negative 1/2 plus minus this whole thing, x plus 4 all over negative 3 all over 2. So that's a big, clunky, ugly situation, okay? But that is algebraically what the inverse is. Now, if you wanted to use the function notation, you could always just put f of x equals negative 1/2 plus minus radical x plus 4 over negative 3. That in and of itself is all over 2. And you could call that the final algebraic representation of the inverse function. All right. So a lot of room to make mistakes there. Obviously, be very careful with your algebra. All right. What else are they asking for? Let's see. They also want us to graph the inverse. Well, we kind of did that before. Now, clearly, it would be a very confusing thing to attempt to graph this, right? So I would say if you're going to graph the inverse, rely on your graph of the first function. Now, the graph of the first function was this, right? I would take into account, if I'm going to graph the inverse, I would take into account the 3 main points. We have a reference point here, we have a reference point here, and we have a reference point. Actually, it should be here. Okay, I drew this dotted line. I'm going to erase that to avoid confusion. I'm going to erase this dotted line because it's not drawn to scale. The reference points are there. Okay, so we have 3 reference points. The vertex, which is at negative 1/2 comma negative 4. We have this reference point, which is at negative 1 comma negative 7. We have this reference point, which is at 0 comma negative 7. And then I would work with the inverse of those reference points. And that's nothing more than switching the x and y values. So negative 1/2 comma negative 4 becomes negative 4 comma negative 1/2. Negative 1 comma negative 7 becomes negative 7 comma 1, which would be, by the way, right here. All right, so let me erase this dotted line. So, and I'm going to actually graph negative 7 comma negative 1. Well, that would be right there. And then this 0 comma negative 7 would give us a negative 7 comma 0, which is already represented there. So to graph this thing, I would only take into account the 3 reference points, switch the x and y coordinates, and then draw the parabola from there. Okay, that's one way of doing it. You could also reflect across this dotted line as well. So I do hope that makes sense. Hopefully that is helpful, and that covers this one. Okay, finally, what do we have? Graph the function using your TI-89 calculator. Copy the graph. Okay, so I'm going to assume my student knows how to do that. Let's actually zoom this in a little bit. Copy the graph. State the type of symmetry, if any, the function has. State the function if the function is even, odd, or neither. So once again, if a graph has symmetry over the y-axis, it's even. If the graph has symmetry about the origin, it's odd. Okay, so looking at this first one, there is symmetry at the y-axis, yes, so it's even. Okay, another way of knowing that it's even is you can plug in negative x and see if you get the same function all over again. We already covered that before. So that applies there, so good job to my student with that one. Plugging this one turns into this, and it's symmetrical in and of itself, right? It's a shape that's symmetrically, like geometrically, but it's not symmetrical about the y-axis, because otherwise this stuff would be perfectly reflected across the y-axis, and it's not, right? So this is not symmetrical about the y-axis. It's also not symmetrical about the origin either. Being symmetrical about the origin is kind of like rotating the shape 180 degrees, by the way, for the record. That's a way of thinking about it. But nonetheless, this is neither, so therefore it's neither odd nor even as well. So good job to my student with that. And this one turned out to be and I hope you like that noise. And this is definitely symmetrical about the origin, because if you think about it, this could be rotated 180 degrees and it would land perfectly right there. Another way of thinking about it is it reflects across this dotted line over here, and then you flip it again across this dotted line, and it ends up becoming that. That might not make sense. Maybe the 180 degree rotation is a better way of thinking about it for you. But the fact that it's reflecting, or rather symmetrical about the origin, is proof that it's odd. It's definitely an odd function. So my student did a good job here. Also, we could know that it's odd by replacing the x's with a negative x, and you would realize that this would pump out a negative version of the original function, and therefore it would be odd. All right, so my student looks pretty solid there. This could be seen as easier because you're allowed to graph it using your TI-89, and sometimes that makes things a little bit easier. But nonetheless, that is my review for my students' review sheet. Hopefully that was helpful. As usual, let me know if you have any questions, and check out my website, sagemathtutoring.com. And good luck to my friend. Best wishes on the test coming up soon.